Okay, so let's see. All right. So 3.3, the Cramer rules. So a lot of calculations in Cramer rules. So listen carefully. Rule. Uh, so the goal is to solve the matrix system. A x bar is equal to B. So any for any matrix B in Rn space. Okay. All right. So here we assume that A is n by n matrix. A is on n by n matrix. All right. So so far we when we solve the matrix system for any for given the vector B, we had to row reduce the augmented matrix, right? Okay. It's simply basically we apply the Gaussian elimination. So using the Gaussian elimination, or we can say reducing row reducing to get echelon form to find the solution, right? But that's not the kind of efficient way for solving system for any choice of the column vector B. So we want to find or develop the method for solving matrix system for any choice of column vector B. So that's the Cramer rule is the one of that method. Okay, so to do that, okay, so let me introduce new notation. Okay, so for any n by n matrix, okay, matrix A, okay, and B is in Rn space. Okay, so we just say A I B. So that means replacing the ith column in matrix A with by the column vector B. Okay, so A1. Okay, the A1, A2, these are column vectors in matrix A. Okay, so let's say A is the A1, A2 through the AN. So okay, and for example, A2 is column vector. A21, A22 through the A2N. Okay, so this is n by 1 column vectors. So replacing the ith column in matrix A. Okay. So with the B vector B, then we'll get this. Here, there's a vector B bar. That's the ith column. Okay. And then AN. Okay. So that's the new notation. We're gonna use that notation to build up the Cramer rule. So theorem 7, 3.7. Okay, 3.7 introduce Cramer rule. So let's say A be invertible definitely. The n by n matrix. Okay. For any vector B in Rn space, right? Rn space, the unique solution, since A is invertible matrix, it means that for any choice of vector B, it should have there exists to make a solution of that system, right? Right here. That X bar must be a unique solution, right? The unique solution. Because A is invertible. Okay. What does that mean? The A is invertible. That means this system has unique solution, and then A has n pivot columns, and then those columns are independent, linearly independent, right? is it? Is there a lot of equivalent statement in a invertible matrix theorem, right? So please keep in mind that the invertible matrix theorem. Okay. So for any so this is the side story, and then from here the unique solution. The solution x bar of ax b as entry given by xi is equal to determinant of ai and b. So what does that mean? That means what does that mean? So first one, a of b bar is what? This, right? And then that's the this is determinant of the sum matrix by removing ith, isn't it? Ith row and column, isn't it? Determinant of that matrix. That matrix. So the top one means the determinant of that matrix divided by just determinant A. So I goes 1 through the n. Okay. So that's the Cramer rule. This is formula. Okay. Let me use other color. Okay. So let's see proof. Ooh, okay. So let's say first one A. Okay. The columns of matrix. Sorry. In the matrix A, let's see the columns of matrix A. Mm, A1 through the AN. Okay, through A. And let's say the columns of n by n identity matrix. Okay. Columns of n by n identity matrix. Let me just say I sub n. That means n by n identity matrix by E1, E2 through to En. Okay. So these are what? So for example, E2 means what? So it's 0, 0 through to 0 and 1. Okay. And then 0 through to 0. So all the entry in a column vector is 0 except for um, the second, actually this is second, right? Except for second entry is just 1. Okay. That's the E2. So this is the sorry, this is the second entry. Okay. Then EI is what? It's going to be ith entry is 1. Then all other entry is 0. So we got this one is ith entry. Okay. So we can we can say that each columns of ith matrix is like this. Okay. E1, En, and the A1 through An are just columns of matrix. Okay. So now then A then means it means that A is what? A1 through the An. Okay. What's the size of the matrix? N by n, right? And the In is what? E1 through the En. Okay. So now what are you going to do? We do this. A times, we do matrix multiplication. A times I of x1. So what is this? What does that mean? It means that this is a matrix obtained by replacing ith column of the identity matrix by x bar, right? So this is the matrix, right? Obtained from I by replacing ith column of I x1. Okay. So now then it means that what? This is equal to A times this is equal to well, A times N. This is 1, 0. Let's just, extract the this one, that matrix. 0 and a 0, 0 and 1, 0 and a 0. Through here and then 0 through the 0 and then there is I right here. Oh, 1. All right, 1 and 0. Oh, sorry, that one. X1, sorry, X2 through the xn 0 through the 0 and 1, 0, 0, something like this. The 0, 0, and 1, isn't it? This is the I column, right? Isn't it? Then what does it look like? Anyone can figure out what is this? A times the matrix. This is the I of x bar. What was that? All right, so A times that matrix I sub I of x bar, it turns out that that matrix whose columns are like this: A times E1, A times E2 through the, and then the ith column is gonna be should be A times X, and then A times E sub I plus 1 through the A times E sub N. Okay, so now then we know that what A times E1 is nothing but the first column of matrix A. So this is equal to A1. The second column is nothing but A2. And then the ith column AX bar is what? That's a B, right? You see? And then this is the AI plus 1 through the AN. Okay. So this is equal to what? AI of B. Right. So which means that we can rewrite this matrix obtained by replacing the ith column of matrix A by B as A times I sub I of X. Right. Okay. So we start from this. You got it? We start from that one. We end up with what? This. So these two expressions are identical. Okay, that's what I'm saying. Okay. Then by the property of determinant. Okay, let me say multiplicative. Okay. Property of determinant. Okay, just say the DET stand for determinant. Okay. Do you know that determinant? Determinant of the matrix. What it is? What's that? Determinant of A times B is equal to determinant of A times determinant B. Got it? So using this one, determinant of AIB, right? Or this is equal to A times identity matrix of X is equal to determinant of what? Of A times determinant of II of X. Okay. And then that is equal to, yeah, this is equal to that one. Yeah. Okay. So this is equal to, determinant of AI of B. Okay. So, okay. So now then let's figure out, okay. Let's figure out this one. I'm wondering this one. So this here, this one, determinant DET of I sub I of X bar is equal to, what is the I of X bar? Right there, right? This is I sub I of X, right? So let me bring this one here. This is 1, right? Then here's 1. There's 1 through the what? There is an X of I, right? Okay. And then here's X1. x2, x3 through the xi, then xi plus 1 through the xn, right? Okay, so and then this is 0 through the 0. And here's all 0. Here's all 0, right? And then here's a 0 too. Okay, and then here's a 1, right? Okay, and then 1 through the 1. Here's a 0, and then here's a 0. I mean, here's a 0 too. Here's a 0, and here's a 0. Okay, so I mean, right there, this one. We choose this one to find out determinant of this. I'm going to use the cofactor expansion to figure out determinant of that matrix. Okay, so to apply the cofactor expansion, we need to choose either a row or column, right? Including the most 0, right? So I'll choose this one. Okay. Then this is the that's the x bar, right? And then in what ith column of matrix I. I sub n actually, I sub identity matrix, right? And then that's the ith row. Okay. All right. So yeah, we're gonna make a cofactor expansion. Making a cofactor expansion along the ith row. Then determinant of I sub I of x bar is equal to what? See, 0 times what? What's the cofactor expansion? Anyone can tell the formula of cofactor expansion? Let me wrap it up this lecture. So we got yeah, so a times a sub I x bar turns out to be this, right? So it turns out that a times I sub I of x is equal to this. Now using the determinant, the multiplicative property of determinant, determinant of this one is equal to, I mean, we can separate this one as product of two determinant A and determinant I sub I. And this should be equal to determinant of A sub I B. And then what is the determinant of I sub I x? This is the determinant of this one. Sorry, it should be just vertical line, not the bracket. Sorry, this one. And then we choose I row to make a cofactor expansion. Okay, so along the I row, determinant of I sub ix is equal to minus 1 to the I plus 1 times 0. 0 is from that first entry in I's row. The determinant of cell matrix, removing I's row and then first column. Okay. And the plus minus 1 to the I plus 2 times 0. 0 is from the second entry in I's row times determinant of the cell matrix, deleting second column in the I's row, and so on. Since the the value of entry is 0, the first term, second term through the I minus 1's terms is gone. And then I plus 1 through the nth terms is gone because of the entry 0, as you can see that in I's row. So this term is going to be the alive, okay? So I minus 1 to the I plus I is just 1. And the xi times determinant of this guy is just 1 because the look at the cell matrix. Cell matrix removing the i's row and then i's column, we're gonna get the identity matrix. So identity determinant identity matrix 1. So this should be xi. So this one is equal to xi. So this the plug in this one into this multiple property, then xi must be equal to this guy divided by determinant A. So that's the Cramer rule.